Okay, so good morning, good evening, or whenever you're watching this, good day. This is the answers to our exercises from Lecture 7 on plane areas. So I hope as we go through this also clarifies your questions or whatever it is that you're so confused about plane areas and the application of integrals onto this field. So I made a presentation solely for the answers to the exercises on Lecture 7. So the first item is to find the area between the curves y squared equals 2x plus 3 and y equals x. Now the thing about this problem is that, well, the problem about this problem is that we don't know what the curves look like. So the instant solution to that is to plot the curves. First, let's plot y squared equals 2x plus 3. In standard form, this is a parabola. That is y squared equals 2 parentheses x plus 3 over 2. So this means that this is a parabola whose vertex is at negative 3 over 2, 0. So the coordinates is at x equals negative 3 over 2 and y equals 0. Those are the coordinates of the vertex of the parabola. But if you don't trust me just by the standard form, then feel free to plot the points, and we can do that. So here's a table. I tabulated the values where at x equals 0, we get the value of y squared, and that is equal to 3. So we get the value of y at plus minus square root of 3. So now we have 2 points. That's x equals 0 and y equals square root of 3. And x equals 0, y equals negative square root of 3. Now we equate y squared equals 0 just so we know which part of the curve intersects with the x-axis. So at y squared equals 0, that is 2x plus 3 is equal to 0, or x is equal to negative 3 over 2. Plotting those points, again, we have positive and negative square root of 3 at x equals 0, and x equals negative 3 over 2 at y equals 0. So now we have 3 points, and if you're not comfortable with that or you don't trust these 3 points, then feel free to add more. But if you think you get the picture already just by the 3 points, then good for you. Now let's look at y equals x. This is a pretty common curve, so I'm pretty sure you have a general idea of what this looks like, but if you don't, then let's plot the points. So at x equals negative 1, y equals negative 1, x equals 0, y equals 0, and at x equals 1, y is also equal to 1. So we have those 3 points there. So if you notice, the 3 points earlier are marked green, while the 3 points this time or for this curve, are marked purple or violet. So here we can see that it's a straight diagonal line. And now that we have a general idea of what the two curves look like, now we need to get the points of their intersection, or where do the two curves intersect. So how do we get that? We equate the two curves, or the two equations representing the curves. So here it looks like it is easier for us to use y equals x and substitute the value of x back to the first equation, that is y squared equals 2x plus 3. So substituting y equals x back to the first equation, we get y squared equals 2y plus 3. Transposing to the left side of the equation, we get y squared minus 2y minus 3 equals 0. And this is a quadratic equation where we can factor it as y minus 3 multiplied by y plus 1. This means it is 0 at y equals 3 and y equals -1. Which means these are the two values of y where the two curves intersect. So at y equals -1, x is equal to -1, and at y equals 3, x is equal to 3. And those 2 points are shown here. If you plot 100 more points, then you will see that it looks something like this. Now we're ready to draw the differential rectangles. And it looks like it would be easier for us if we considered horizontal rectangles or horizontal differential rectangles. So just a reminder, and something that I failed to mention in the lecture slides, is that when we draw the differential rectangles, it is always radiating from the y-axis if we're talking about horizontal rectangles. And for vertical rectangles or vertical strips, those will always be radiating from the x-axis. So for example, for these two curves, we decided that we are going to use horizontal strips. So here we see a purple strip from the y-axis to the curve y equals x, and a green strip from the y-axis to y squared equals 2x plus 3. And their difference would be the blue strip that would be representative of the differential area at that point, or at that value of y. We get the violet strip from the y-axis to y equals x, and the green strip from the y-axis to y squared equals 2x plus 3. All the areas calculated from the y-axis to the positive x is considered a positive area, and all the areas calculated from the y-axis to the negative x direction is considered negative area. So it doesn't matter that we are subtracting the right curve minus the left curve, as it will result to, that is the blue strip between the two curves. So the goal of the differential is to sum up all the blue strips that would represent the area between the two curves, from the lower intersection point to the upper intersection point. So the formula for the horizontal strips is a equals the integral of xr, that is the curve on the right, minus xl, that is the curve on the left, from c to d. And xr is represented by phi of y, and xl is represented by gamma of y. So xl, or the curve on the left, or gamma of y, is y squared equals 2x plus 3. We need to write it in terms of y. So x is equal to 1/2 parentheses y squared minus 3. And that would be xl. And y is equal to x would be our xr, or the curve on the right. So it's always right minus left when we're dealing with horizontal strips. So now we have the curve on the right, the curve on the left. The next thing that we need is the next thing that we need would be the upper and the lower limits. That is c and d. So our c would be y equals -1, and our d would be y equals 3. Again, these are based on their points of intersection. So now we finally have the formula that would represent the area between the two curves, that is from -1 to 3. Let's now solve this integral. So area is equal to the integral of y minus 1/2 parentheses y squared minus 3 from -1 to 3 with respect to y, and distributing 1/2 into the parenthesized expression, we get -1/2 y squared plus y plus 3 halves. Evaluating the integral, we get negative 1/2 times 1/3 y cubed, we just used the power rule on y squared, plus 1/2 y squared, we just used the power rule on y, plus 3 halves y, so we just used the rule on the constant or on integrating constants. And again, this will be evaluated from negative 1 to 3. So just simplifying the equation. So now we're evaluating from negative 1 to 3. That is negative 1/6, 3 cubed, plus 1/2 3 squared, plus 3 halves of 3, minus the entire bracket containing negative 1/6 of negative 1 cubed, plus 1/2 of negative 1 squared, plus 3 halves from negative 1. We get this value. And if you're not confident with your arithmetic skills, then feel free to use a calculator at this point. But again, you need to practice. So you can get the common denominator, that would be 6 of everything. And you would end up with A equals 16 over 3, or the area between the two curves. Y squared equals 2x plus 3, and y equals x would be 16 over 3. But again, you can opt to use vertical strips. Feel free to do that and confirm if you also get 16 over 3. Just make sure that you set your limits. Again, determine the upper and lower limits. That would be the leftmost point and the rightmost point for vertical strips. So you can use area 1, that is the curve that is enclosed by y squared equals 2x plus 3 from x equals, I think that would be negative 3 halves, to x equals negative 1. And then area 2 would be from negative 1 to positive 3. So those would be your upper and lower limits if you're going to use vertical strips. And again, make sure to express the equation in terms of x, since now we're dealing with vertical strips. And the total area would be A1 plus A2. Phew, congrats! You finally are more confident with using horizontal and vertical strips. Now, let's move on to exercise 2, and that would require us to use polar coordinates. So exercise 2, find the area of the upper half of the limathon. Yes, that's a limathon. Our college teacher, I think they pronounce it as limathon, since that would be more understandable. So find the area of the upper half of the limathon given by the equation r equals 1 plus 2 cosine theta. Now, it doesn't actually matter if we know what a limathon looks like. What matters is we know how to plot. So let's plot. Let's go over this one by one. At theta equals 0, we evaluate r, 1 plus 2 cosine theta, and cosine theta is 1 when theta equals 0, so r equals 1 plus 2. That would be 3. And at theta equals pi over 6, that would be 1 plus square root of 3, or 2.73. And at theta equals pi over 3, we get r equals 2. At theta equals pi over 2, we get r equals 1, since cosine of pi over 2 would be 0. At theta equals 2 pi over 3, we get 0. Now, at this point, we actually reached the upper half of the limathon, or we already completed the upper half of the limathon. But just to show you that we would be going over, or we would be going beyond the upper half of the limathon if we go beyond 2 pi over 3. Let's look at the value. At theta equals 5 pi over 6, r would be equal to negative 0.73. And as you can see, that would be part of the lower half of the limason. So for the upper half of the limason, we only need to evaluate the area from theta equals 0 to 2 pi over 3. But if you're curious what the entire limason looks like, it looks like this. So it has a hoop in the middle, a loop, sorry. But again, we only need the upper half of the limason. So now we can use differential sectors so that we can calculate the area of the upper half of the limason from theta equals 0 to theta equals 2 pi over 3. Are you ready? So recalling our equation, so unlike the Cartesian or rectangular coordinates that we just input or plug in the equation or the equation of the curve, that is the right minus left or upper minus lower. Here we need to square the value of r and multiply it by 1/2. So the area for polar coordinates is equal to 1/2 of the integral of r squared d theta from alpha to beta. So r is equal to 1 plus 2 cosine theta. And our alpha and beta would be theta equals 0 and theta equals 2 pi over 3. Ta-da! So now we have the expression or the equation that would represent the area of the upper half of the limason. If you're observant enough, then you would notice that this is the item on the quiz, item number 3 on the quiz. And I also uploaded the PDF file for this problem. But let's go through it. So area equals 1/2 of the integral of 1 plus 2 cosine theta squared d theta from 0 to 2 pi over 3. Just expanding the integrand, that is 1 plus 4 cosine theta plus 4 cosine squared theta. And rewriting cosine squared theta into a more integrable expression, or into a more easily integrable expression, that is 1/2 of 1 plus cosine 2 theta. Distributing 4, we get 1 plus 4 cosine theta plus 2 times 1 plus cosine 2 theta, and further distributing 2 into the parentheses. Now we can join 1 and 2 since they're both constants. We get area equals 1/2 the integral of 3 plus 4 cosine theta plus 2 cosine 2 theta from 0 to 2 pi over 3. Evaluating the integral, we get area equals 1/2 times 3 theta plus 4 sine theta plus 2 times 1/2 sine of 2 theta, evaluated from 0 to 2 pi over 3. So evaluating from the lower to the upper limits, that is 1/2 of 3 times 2 pi over 3 plus 4 sine of 2 pi over 3 plus sine 2 times 2 pi over 3 minus 1/2 of 3 times 0 plus 4 sine of 0 plus sine of 2 times 0. So the entire right side would equate to 0. We get area equals 1/2 of 2 pi plus 4 times square root of 3 over 2 minus square root of 3 over 2. Simplifying, we get area equals 1/2 times 2 pi plus 3 square root of 3 over 2. And that is simply A, or area, is equal to pi plus 3 square root of 3 over 4. And that is 4.44. So congratulations! Now you can use polar coordinates more freely. So again, if you want to practice some more, then feel free to look up more equations in terms of r and theta. And again, review on the angles and how to plot graphs on the polar, using the polar coordinate system. So there. good luck and thanks for watching.